Alkanes are very unreactive, but one reaction they do undergo is free radical substitution. Substitution part is clear to see from the equation. One hydrogen has been removed, it's gone from H6 here to H5, and in its place one of these bromines has joined on to the molecule here to make a bromo compound. The hydrogen that's come off has joined up with the other bromine to make HBr, so effectively there's a swap or a substitution. This is the case in all free radical substitution reactions. You take a hydrogen off and you put on a halogen. It could be chlorine, bromine, iodine. Right, you need to know the mechanism of how this happens. The mechanism is a series of steps showing the path taken by the electrons in the reaction. So in free radical substitution it's split into three parts: initiation, propagation and termination. So the first step then, initiation. Because our halogen here is bromine, bromine is what we use here. If it was Cl2 it would be Cl2 down here. So bromine, when exposed to UV light, undergoes homolytic fission. So we haven't got a positive and negative ion here. What we have are two free radicals. The bond between these bromines is split evenly. Okay, so each one gets an electron, and that's an unpaired electron, and we call that a free radical. So a free radical is a species with an unpaired electron, and free radicals are very, very reactive, and that's why alkanes react with them. So next step then. Next step is propagation. Propagation always has two steps in it. So our ethane, which is the alkane we want to react, reacts with our free radical, and the free radical removes one of the hydrogens to make HBr. Always takes one hydrogen away to make HBr. That is no longer a free radical now, it's paired up. But here we've been left with a free radical on what's left, C2H5. Now that has a free radical and is very reactive itself, and that then reacts with a bromine molecule, Br2. Now this part quite often confuses people and they say, where's the bromine come from? Not all the original bromine in the initiation step will be converted to the free radical. A lot of it will stay as Br2. Okay, but we don't need many bromine free radicals for this reaction to occur, because it's regenerated later on anyway. So here and here, this reacts with bromine, takes one of the bromines away to make C2H5Br, which is the product we wanted, and then the bromine free radicals regenerated to redo this step again. So that's why we don't need many of the bromines to split up homolytically, because it's regenerated in the process anyway. If you combine these two equations together, putting all the reactants and all the products together, because this would be on both sides of the equation, it would cancel out, and so will the bromine free radical, and you're left with the overall equation that we started with anyway. So this process of propagation is what causes the reaction to happen, really. It's the main part of the reaction. Okay, now this propagation will carry on endlessly, because we keep regenerating until eventually we either run out of ethane or we run out of bromine. But another way you can stop is by termination. So termination's the third and last step in the mechanism, and that's when two free radicals combine. So here, if you think of all the possibilities you could have the two bromines reformed to make Br2, we could have the C2H5 and the Br formed C2H5Br, or, this is one people forget, the C2H5 forms C4H10. There are always three possible termination reactions. Now this reaction, all free radicals, not just this particular one, but all free radical substitutions have a low atom economy, and that's because you produce a mixture of products. If you look back at that termination step, we wanted to produce this, but we didn't want to produce this one. Okay, so I mean this can be used up anyway in the reaction, but this would lower our atom economy. Another problem is that even the thing we produce, C2H5Br, could react with a bromine free radical again to make C2H4Br2, and it can happen again and again and again, could end up as C2Br6. Okay, it's hard to control that and stop that happening because free radicals are so reactive. So we would end up with a mixture of products, the one we want, and then other ones with multiple substitutions rather than just one.